Hi, my name is Lucas Gallegos. I am a second year at Wentworth. I am the events coordinator, so I am in charge of scheduling and posting all events for the club. My major is mechanical engineering, so I am in charge of managing things like layering the carbon fiber and applying the fins.
Hi, I'm Aiden. I'm a second year electromechanical major. I am the treasurer currently for Rocket Club. That mainly just deals with budgeting for the materials for the rocket, the motor, the tubes, supplies for events, things like that. Generally, I just help around with the rocket, sanding, electronics, 3D printing. For this project, I was more of the main designer, figuring out the motors that we want to use, the size of the tubes, the length of the rocket, things like that.
Hi, my name is David Billia. I'm a former founding member of WIT SRT. I'm now a graduated student and the EEE L3 mentor for the team, and I oversee construction.
Hi, my name is Josh Allen. I am a sophomore in computer science, and I am the social media chair for the club, and I also oversee all of the electronics. So anything, the GPS, the flight controls, the controls for when the parachute releases and such, that's all my domain, so I deal with all of that.
Hey, I'm Adi. I am a freshman electromechanical engineering major, and I am the WIT SRT club historian. When we're building the rockets, I mostly help work on the fiberglass fuselage components.
Hello, my name is William Biggs. I'm a physics major, and my goal on the rocket team is to gather sponsorships. This year, one of our rockets is planned to squeeze as many points out of the competition as possible, so we're really hoping to try and get the first place with that rocket.
Hello, my name is Vivian Marr. I'm the president of Wentworth Sounding Rocket Team. I am a junior in construction management and an L2.
We'll be using the fluctus to ignite our sustainer, and then our thruster will ignite 1 second after booster burnout, and the sustainer will burn for 2 seconds. For the safety of arming, our air start velocity lockout is 200 feet per second, and our air start tilt lockout is 12 degrees and may be made tighter depending on the air conditions. If the second stage motor fails to ignite, both the booster and the sustainer have their own redundant deployment electronics that will put out a drogue and main parachutes as if it were a single stage flight. All deployment electronics will be armed with a twist and tape wire method. Our sustainer motor igniter will be installed vertically, the booster will have rail guides and will be installed horizontally, and the rail will be tipped up and the rail will be aimed with the rail stabilizer. Then we will install the sustainer igniter and connect the sustainer igniter to the wires running down from the avionics bay. Then we will install the sustainer without rail guides. Then we will arm the sustainer electronics, then arm the booster electronics, then insert the igniter and check continuity for the whole system.
For Argonia this year, the team had two different ideas for a rocket. We wanted a more, option one was a more optimized, higher flying rocket, and the second option was a more conservative but more successful rocket. And we ended up choosing the second one, just between helping teach our younger members more fundamental basics and making sure we have an actual good successful rocket this year, for our members and for our school. And so with that, when we're looking at our scoring, we have our apogee, we have our total impulse, and we have our payload, which would be the golf balls. So we saw that around 10 golf balls was where the multiplier had plateaued for the scoring, so we ended up choosing around 10 for our payload. For the rocket, we had chosen the motors J1799 and K700. This would leave us with a total impulse of about 3,475.8. And then using those motors, we designed the rocket around it. We had a 3-inch diameter rocket with a total length of about 67 inches. And with these motors and our design, we simulate that we're going to have an apogee around 13,000, and this will give us a score about 44,000, which we're pretty happy with. This will allow us to build which we think a very successful rocket that'll get the team's name on the score this year.
When we started this school year, we realized that we had a lot of our team graduating out. So we took a look at our upcoming class and we realized that we needed a project to really teach the new members how to do all the parts from designing a rocket to fabrication. When we started that project, we called it the New Member 2 stage. The first step was buying cardboard tube. We wanted it to be low price and give them most amount of learning opportunities. So we did cardboard tube, and then we did a fiberglass layup on it using a fiberglass sock. A few of us have worked at a epoxy shop before, so we've had a lot of time to work with these materials, and we're super excited to pass them on to our newer crew. After the fiberglass sock was on, we then laser cut fins using our college's makerspace. And then with these fins, we were able to do a tip-to-tip carbon fiber layup using a full bag and everything.
Go.
We are running identical 3D printed bays for both our booster and our sustainer bays.
And go.
Okay, so for our electronics, we are using a fluctus to control the primary charges, the GPS and tracking, and it is powered by a 2S LiPo battery. For our redundant flight computer, we'll be using the RRC2, which will run on a 1-second delay, firing the redundant charges, and it is powered by a 9-volt battery, and both of these computers are controlled by a twist and tape method. We figured that this would be easier than using switches because when we're ready to arm, we just twist the wires together and we've got a current through the whole thing. And the actual wiring for the computers themselves, we used 2 different colors twisted together to be able to tell what wire goes where. And for a backup GPS system, we're using a Marco Polo radio beacon.